Greetings to all and welcome to a new video about magnetic circuits. This is our example number 5. In the example I will again discuss step by step another example using a magnetic circuit. So let's look at our example. We have the following problem. The following magnetic system is given and we have the following data in it. So we have the geometry, we have the current, number of turns in this coil, and we have the cross section of this system. So it is 2 centimeters by 2 centimeters, which is then 4 centimeters squared. The core material has a relative permeability of 5000, and we have also a gap here which is 3 centimeters wide in this y direction. Okay, what we need to calculate is the following. Calculate the magnetic flux density in the air gap. So in this air gap we need to calculate the magnetic flux density B, which is of course given in Tesla. So how do we start? Let's look at the solutions and we work it out step by step. So the solutions. First we need to of course have a circuit diagram or equivalent electric circuit of this one. Before we move on, let's collect the necessary elements. The magnetic motive force, which is just the source defined by this current, and also the turns ratio is given by F is equal to N times I. So we know the N, we know the I, so we can just substitute the values. We have then 3200 ampere turns. So that is our source in this magnetic system. In addition, we have also the mean path length, which is required to calculate the reluctances and also from there the required magnetic flux density. Now, if you look at this system, we have several mean path lengths. So first L1, I will designate L1 as the path length starting from here and make a route like this and going up to here. So what is this? It is actually 2 times that 8 centimeters, 2 times 8 centimeters, and plus this 12 centimeters. So this is actually height. So that is this, and we have then 0.28 meters. So we have to of course work with meters. In a similar form, we can also do that for L2, which is actually this part of this system. Now we have of course this gap, so we need to subtract from this 12 centimeters. So I have then 0.12 minus 0.03, which is then 0.09 meters, which is just this part of this system, excluding the gap. In addition, we have of course also the right hand side of the system, which is exactly the same mean path length as L1, so L3 is also 0.29 meters. Now the final one is the L gap, which is then this distance, which is already given, so that's just 3 centimeters or 0.03 meters. That's the collection of the mean path lengths. We need these information later on. In addition, we also need the cross-sectional area. We already given that actually in this diagram, but we need to also look more carefully to this gap because there are some issues with fringing. So the cross-sectional areas, first the gap. Now, taking into account the fringing, if you want to take that into account, you will have of course more accurate result. So the way to do that is add the L gap, which is this distance, to each dimension of this cross-sectional area given in this figure. So 0.02 was actually 2 centimeters. You add to that the L gap, and again 0.02, and also add to that the L gap. So what you get for actual the cross-sectional area by the gap is then of course much larger than in this case instead of this actual cross-sectional area. So what we have then just for the gap cross-sectional area is 0.0025 square meters. That's for the gap. Now for the core material, so that's actually for the left hand side, right hand side, and also for this middle part, excluding the gap, it is just A1 is equal to A2 is equal to A3. These are all 4 times 10 to minus 4 square meters. Of course, we need to convert this to square meters. And that is just what it is in terms of the cross-section area. This part is very important to take the fringing into account. Now let's move on and go to continue with the reluctances. We have of course electric circuit. We already said that. So this is the source. We have now here this part, the left part has its own reluctance, R1. This part, middle part, has in series the core material reluctance and also the gap. And we have the right hand side, which is just the core material reluctance, so that's R3. So let's look at it one by one. So what is R1? R1 is given by this formula. Again, this is the path length already given here. This is the relative permeability, 5000 here for this core material. The vacuum permeability, which is then 4 pi times 10 to minus 7 henries per meter, just a constant. And A1 is the cross-sectional area. We already have it here also in this figure. So if you substitute all the values in here, we'll get 111 times 10 to the power 3 amperes turn per Weber. That's for R1, for reluctance here. Now continue with actually the right hand side, or this part is also the same because it has the same path length and also the same core material and also the same cross-sectional area, so that is just exactly the same. So that will also be 111 times 10 to the power 3 amperes turns per Weber. Now continue with R2, that's actually this part, which is of course this, excluding the gap. Now we already know, of course, L2 and also the A2. A2 is just again equal to A1, but L2 is of course a little bit smaller compared to that part of this L1. So if you now substitute all of them, including the values here, we will get 35.8 times 10 to the power 3 amperes turns per Weber. That's what we have now for R2. Now the final one is the R gap. Now that is just the vacuum permeability because there's no core material here, and we have of course the distance of this gap, and also the A gap because that's already calculated here, taking into account the fringing, very important. Now if you now substitute the values, you will get 9.56 times 10 to the power 6 ampere turns per Weber. Now look at these three values. The R reluctance of the gap is much larger than the reluctances in the core material because the magnetic field is actually having more problems to develop here in the air than in the core material. So that's already seen in this reluctance value. Okay, what's the next step? The next step is actually, let's combine these two because it's already a series. So in circuitry you can of course also add two resistors in series. So we will do that here and we just call it RA, and R2 plus R gap will be actually R summation, and that will be then 9.60 times 10 to the power 6 amperes turn per Weber. That will be handy later on. Okay, we need to go to the magnetic flux density, which is actually in this part, and for that we need to have the phi 2. So in order to go to phi 2, we need to have the phi 1, which is sort of the supplied flux here by this source, and it will of course divide that into branches. So once I know phi 2, I can of course then calculate B, which is the relation between the phi and the B and also the cross-section area of the gap. So let's move on to the total reluctance, which will then give us the phi 1. What's total reluctance? Again, a similar formula as in the resistors in the electric circuits. R1 will be in series with this combination, which is just the combination of these two resistors in series parallel to R3. Now we already know that R1 and RA was the series combination of R2 and R gap, and that is now in parallel, which is then this two vertical lines is the parallel notation to R3. If I write it out in different form, which is then given by this expression. Now substitute the values we have here, now 111 times 10 to the power 3 and also the rest of the values, you will get 221 times 10 to the power 3 amperes turns per Weber. That is now the total reluctance seen by the source. Okay, now we have the necessary information to calculate phi 1, which is then the total flux. So the magnetic flux will be then phi 1, which is then the magnetomotive force divided by the total reluctance. Now, if you substitute the values, you will get 0.0145 Webers. That is now the total flux. Now we can use now, as in the circuits, electric circuits, current divider rule. This flux is of course coming from the source, and of course will be partially going also in this R3, but for that we can use the current divider rule in this form. the flux flowing in this branch is equal to the reluctance in the other branch divided by the total reluctance in these two branches together. That's actually shown here, times of course the source, which is then the phi1 source flux. And now if you substitute the values in here, you will have then 1.66 times 10 to the power minus 4 Webers. So much smaller actually than the source. Now we are actually now very close to the final result, which is then the magnetic flux density in the gap. Now we have the magnetic flux phi2, which is also the magnetic flux in the gap. Now we can also use the magnetic flux formula now. B is equal to phi over the area. Now B gap, that's what we want, to phi2, which is then the flux, magnetic flux in this branch, divided by the A gap, which is then the cross-sectional area of the gap. We know all the necessary information, so just substitute the values and you will get 66.3 millitesla, so 0.0663 teslas. And that's now the final result for this exercise. So in this gap we have given this values 66.3 millitesla as magnetic flux density. Alright, this was example number 5 about another circuit having also branches in the magnetic system, and which we use of course also in the electric domain to calculate the required values. If you have any questions about this exercise, please let me know and I will try to answer them as soon as possible. Thanks again for your attention and see you next time in another interesting exercise. Take care.